Hello, everyone. Thank you all for joining this meeting. My name is Moin Borre. I'm the North America representative of IEEE Dielectric and Electrical Installation Society, the Young Professional Group. And today we're honored to have Dr. Craig Miller, the consulting physicist based in Bellevue, Washington. And he's going to talk about his signature topic, flashover of insulators in vacuum. And before we start the meeting, I'm going to talk about a couple of housekeeping notes. First of all, the webinar will be recorded. And if you have a question, first of all, we're going to have about 40 to 45 minutes of presentation by Dr. Miller, and then we'll have 15 to 20 minutes of Q&A. And please feel free to put your question in the chat box, and we'll ask them in the order received. And also make sure, if you're interested, to send out the field evaluation form to earn 1 hour of professional development hours certificates. And as you always know, we have webinars on the second Tuesday of every month. This month we have Dr. Miller, and next month we will have Dr. Greg Stone, who is gonna talk about winding insulation failure. And all the DIS members will receive an e-notice of our upcoming webinars, and make sure to be part of that newsletter. And for more updates and events, please follow us on LinkedIn, which you can scan the QR code on the bottom right of this slide. So Dr. Craig Miller is a consulting physicist based in Bellevue, and this talk, as I mentioned, is going to be about flashover of insulators in vacuum. And think questions you might have in the chat box, or unmute yourself at the end of the talk, and hopefully we're going to have enough time to answer all the questions. Dr. Miller, the floor is yours.
Okay, I'm now unmuted. Good. Okay, let's get my slides. Here we go. Okay, today I'm going to talk about flashover insulators in vacuum. Insulators are used in many applications which require them to support significant voltage differences while exposed to vacuum. The voltage holding capability of a solid insulator in vacuum is usually less than that of a vacuum gap of similar proportions. The vulnerable area is the surface of the insulator, since its bulk voltage hold-off capability normally is better than that of a similar sized vacuum gap. This talk will be discussed as shown here. Basically, common applications of such insulators include underground distribution. Just about all new underground distribution systems built nowadays use vacuum interrupters as the switchgear. High power transmission vacuum tubes are still used for very high power X-ray devices, and of course, large accelerators. Flashover, normally all theories indicate that flashover of surface insulators begins with field emission from the triple point. At the cathode triple junction, often called CTJ, it's the point where the cathode electrode, the vacuum, and the insulator come together. Electrons are emitted from the triple point, usually by field emission or thermal field emission. They then strike the insulator surface, reduce secondary emission electrons, which in turn could strike and have tertiary, and so forth. You begin to get a secondary avalanche along the surface. As the electrons are avalanching along the surface, they induce outgassing from adsorbed surface gas, and with organic insulators, possibly also vaporized insulator material. You have this gas layer above the surface. The Townsend discharge develops and quickly goes to an arc, and that's when the electric breakdown occurs. There's an alternate theory that says instead of being on the surface, secondary electron emission, you have cascades through both shallow and deep surface traps. All indications are that this is a minor's problem, but can be insignificant in particular cases. This is how it goes. Basically, now for measurements, you measure the current, obviously it starts at 0 and then increases steadily. And when the flashover through the gas occurs, it increases exponentially. Anytime you have voltage applied across the gap in vacuum, you can have X-rays. Of course, for a couple thousand volts, they're very weak. But for even for underground vacuum interrupters, which are rated at 24 to 32,000 volts AC, they have to withstand lightning strikes of 100,000 volts or more. And when such devices are built and tested, a significant amount of X-rays are emitted, and you have to worry about shielding from any personnel. When the voltage collapses, of course, the X-ray emission goes to 0. The gas density increases above steadily and then peaks as you get the flashover start and then drops sharply as it becomes plasma. Here's an example of an optical thing. This one you have a grounded electrode. This is a flat insulator, aluminum surface, a high voltage electrode with a needle touching the surface. You can see the discharge begins at the cathode triple junction where the needle is touching. It develops, it finally goes all the way to the anode. Then normally, where the flashover continues, the highest current occurs. You get the flashover propagating along the surface to the anode, and then you get a sudden streamer coming back from the anode to the cathode as the voltage collapse is complete. Now, it turns out that the surface roughness has a significant effect on flashover, effectively because it affects the surface charging. This has been seen, this particular plot is for an organic, but it's seen to occur in glasses, ceramics, and organic. Very smooth surfaces charge the most. As the surface roughness increases, the charging decreases, and depending on, of course, the material and the geometry, at a certain roughness, charging effectively ceases, becomes 0. It's also, this occurs with all kinds of voltages, pulse voltages, AC, and DC voltage. The rate of charging, of course, can vary. An example, for AC voltages, you get a minimum layer as the charging begins. You have a baseline with a trapezoidal component in phase with the AC. This increases, and finally you end up with a uniform surface charge, which turns out to be very similar to the charge that would occur if you apply DC voltage. And as I said, work with alumina and other ceramics, glasses, and organics all show this, though of course the numbers are different. Now, what great practical importance is found that the flashover field, the time delay till flashover occurs, is a strong function of the electric field. For very short pulses, the nanosecond region is an inverse proportion. In other words, the delay is inversely proportional to the square of the electric field. And as it sorry, I don't know why it said I was unstable. It's not. If we get levels off, it's not surprising because if you think about it, the higher the voltage, or shorter delay, but particularly in pulse, if the delay gets to a point longer than the pulse the width, you aren't going to get flashover. So this has to be considered in practical cases. But this is, again, other investigators have found this inverse dependence. But again, leveling off, it's no longer, there's still some dependence, but it's no longer the square. And similarly, if you have RF microwave breakdown, that's proportional to the flashover voltage is proportional to the intensity. Increasing the intensity increases the time delay. Again, for pulse, it's proportional to the steepness. The steeper the voltage, the higher the initial flashover voltage. Of course, this is not surprising because the rapidly increasing pulse, you get to a high voltage sooner, and therefore, if you're going to have a certain delay, which is proportional to the time, it makes sense that the steeper the rise, the higher the flashover voltage. Now, if you look at it overall generically, overall, from the nanosecond region out to the microsecond region and millisecond, the flashover voltage decreases with increasing pulse length. Typically around the millisecond, depending on the geometry and the material, you find 3 parameters. Unusual, but has been seen, the voltage now increases to a DC, usually not quite as high as a very short pulse, but higher than a medium length pulse. Most common, it just continues to decrease slowly out to DC, which is the lowest voltage. Unfortunately for engineers and power people, a very common one, the voltage decreases to a minimum right around power frequency, 50, 60 hertz, and then increases, sorry about that. And then increases out to DC. Now, if you want to talk about conditioning, it's a phenomenon where if you apply a voltage to an insulator and you get a flashover, you then apply the same voltage and normally you won't flash over. If you have to raise the voltage somewhat higher to get a flashover. This is called conditioning. It has been seen with effectively all kinds of pulses. Pulses, AC, DC, AC and DC. You start out with an initial set of device, insulator, whatever geometry. You get an initial flashover, subsequent flashovers are higher. Eventually you reach a limit, but this is of course of great importance, particularly practical, because often devices are built, assembled and tested before they go into service. And the testing can improve the hold-off voltage significantly, and very often for applications where your device is kept sealed, the persistence and improvement in hold-off voltage persists. It turns out if you have a flashover, very low energy flashover, it takes quite a while, but the condition to the highest voltage is say 25% increase. The greater the flashover energy, the lower the decrease, but it also conditions much faster. Very low energy can take a couple hundred pulses. Higher energy can take maybe just a couple dozen to condition. So this has to be considered, when you're building and testing a device. But it is found there's an inflection point at which point further increases energy, rapidly less improvement, continuing increase and no improvement at all, and then a decrease. In other words, up in this region, subsequent flashovers are less than initial, and you can get to the point, if you get a flashover, it permanently damages the surface and it cannot hold off voltage. But I say conditioning has been seen by just about every time you're having flashover in vacuum. You have to consider it, and it can be a very practical use. As I mentioned, one of the critical things in insulator design is its geometry. The most common design is a cylinder. The also common are positive and negative cones. Here are some other designs. So, went back again. There we go. This are corrugated. It turns out it can be very useful to insert electrodes into the ends of the insulator to improve the flashover voltage, or designing the electrodes to shield the ends of the insulator. Many applications of flashover vacuum, the vacuum is on the inside, we call an internal cylinder, and the outside is now typically either insulated by solids, oil, or in some cases, high pressure SF6. Normally, however, the flashover weak point is still the inside. Another very common one is one I did a fair amount of work with, is an inverted corrugated cylinder. In this case, the corrugations are on the inside. Now, it's also found, of practical importance, the surface flashover voltage is a function of length. For very short lengths, it's proportional to the length, but as you get longer lengths, it can be just a few millimeters and longer, it is less than proportional, and for longer insulators, it's proportional to the square root of the length. This is very similar to what is found for pure vacuum breakdown. It has to be considered, and we'll talk a little bit about, this is a consideration, and particularly large accelerator insulators, where you have more than one, instead of having one long insulator, you have several short insulators. It's a trade-off. A short, 5 short insulators with the same total length will have a higher hold-off voltage than the length in, because of the very short insulators' proportional length. As it becomes longer, it becomes less than proportional, and for the longest, proportional to the square root of the length. But it also turns out the more insulators you have more triple junctions and more weak points. So it has been found there's usually various workers have found in long insulators, there's an optimum number. Like for one, I know for large insulators, they tested for one or two, or 2 or 3 actually, if flash insulators, it improved the hold-off voltage. 3 or 4 was the optimum, and then 5 or 6 it dropped off again. And I said, positive and negative cones are important, and actually it's a function of cone angle. This is down in the nanosecond region. You see cone angle is 0. If you have a positive cone angle, it increases the hold-off voltage, because with a positive cone, the electric field is now tends to take the electrons away from the surface, which means it's somewhat harder to have an avalanche, and therefore you need a higher voltage to get flashover. Conversely, for the slightly negative insulator, you're bringing electrons back to the surface quicker, which reduces flashover. But as you continue to decrease the cone angle or increase the cone angle, you're bringing them back very rapidly. So they're striking the electrons are striking the surface with less energy, and thus improving the hold-off voltage. But again, it's not quite as good as the high voltage. Interesting, you see here the peak is about 45 degrees. And you see the improvement is greater for 3 nanoseconds than 50 nanoseconds. You find out that actually it's greatest for pulse. The effective cone angle is less for longer pulses than AC. But even down at power frequency, while it's less of an improvement, it's still significant and has to be taken into consideration. And the one postulate for this is the effect of the cone angle on the electric field at the triple junction. Calculation for particular design, if the electric field is 1, it decreases with increasing angle, coming to a minimum of about 45 degrees. And as seen previously, for that particular setup, 45 degrees was the maximum hold-off voltage. Oh, darn. Hopefully that's the local phone isn't doing it. I'll take care of it. Sorry about that. The again, also calculations of the behavior of electrons, actually making plots of the trajectories of the electrons like emitted from the cathode triple junction, again indicated the advantage of positive insulator angles and predicted the lowest flashover voltage for angles, 5 to 30 degrees. Again, as I mentioned, representative results for tests with cylinders and the positive and negative 45-degree cones indicate the effective cone angle is greatest for short voltage pulses. But again, the modest increases seen for power frequency can still be significant. Think back to one method of changing the field near the insulator, especially the triple junction, is to put metal inserts into the ends of an insulator. In other words, make the electrodes come into the ends of the insulator. A related method is shaping the electrode to partially reduce the field at the triple junction. And one particular design showed deeply recessing the insulator into the cathode increased the hold-off voltage for microsecond pulses by about 50%. This particular shows the diameter of the insulator. The insulator flashover voltage decreases somewhat with diameter. These results are for organic insulators, but similar results have been seen with ceramic and glass. Well, if you think about it, it's reasonable because the weak point is the cathode triple junction. If you're increasing the diameter of the insulator, you're increasing the length of the cathode triple junction, and therefore you're improving, having a number of weak points. Oh, I forgot to mention one way we think conditioning occurs is when you have a flashover starting at the triple junction, you destroy the weak point. And so the next flashover has to be at the next weakest point, but in other words, slightly stronger. Also, it can be there's some gas desorbed on the surface. When you have a flashover, the gas is desorbed if there's less gas. So conditioning we think is occurring is because you're burning away weak points on the triple junction. Okay, here's a next two slides. I'm going to talk about relative permittivity. The permittivity of an insulator, or the relative permittivity of an insulator, is the relation is between the ratio of the permittivity of an insulator to the permittivity of a vacuum or free space. K of a vacuum, so therefore the relative permittivity of a vacuum is 1, and all materials have a permittivity higher than 1. It's extremely large for metals. So it turns out that materials with higher permittivity tend to have lower hold-off voltages than more moderate permittivities. I'll get into a little more detail. But because this is known, some workers tested, they have the dielectric, the particular insulator between the cathode and anode, but they found if they put a layer of dielectric insulator material with a relative permittivity higher than that of the dielectric, and then perhaps more layers, each layer is a higher dielectric constant, and the one closest to the electrodes has the highest. If you make it, it's more complicated, of course, but insulators like this will have a higher hold-off voltage. And one it's in my paper, but I'm not showing it here. One found there was an optimum of about 3 insulators layers caused the highest hold-off, significant increase, and then it's decreased again. Okay, now the reason the relative permittivity is so important is to show a sketch here. This is the sketch for a particular device. This is with ceramic. Here's the cathode, the ceramic, which is aluminum ceramic, which is a relative permittivity of 10, and a vacuum. If there's a perfect joint at the cathode triple junction, the equipotential lines are, you can see, are uniform, and therefore the electric field is constant all the way along the insulator. Unfortunately, the insulators are built by humans, and it's almost impossible to have a perfect joint, particularly with ceramics. At the electrode, you have a small void now, an extremely small void, a fraction of a millimeter, or even microns. The problem is, the problem is, no matter how tiny the void is, in the void, the K is that of relative permittivity is 1, that of vacuum, and next to it is the insulator, which is a higher in the case of, is 10 times higher in the case of alumina. You get a significant concentration of field lines, of not field, equipotential, which causes an increase in electric field right at the cathode triple junction, and thus reducing the holdout voltage. This is highly undesirable. We found out, however, a way to do. Sorry about that. We found out that it's, God, darn it. Okay. We found out that a significant way to decrease it was to apply penetrating metal ion. Normally, to assemble, aluminum doesn't assemble very well into devices. Normally, what you do is typically you want to braze the aluminum into a device, but bare aluminum doesn't braze very well. You apply a metalize to the surface of the insulator that you want to braze, normally the end. It turned out there's various metalizes. Turned out we used the moly manganese titanium metalize, which what happens is typically you end up with a layer of molybdenum on the surface of the alumina, and the manganese titanium penetrate into it. We didn't realize that at first. We found out that what was going on. And actually, because we found, it just happened, we were using a moly manganese titanium metalize worked the best of all the various metalize. And we found that what happened was the manganese titanium was penetrating typically into the ceramic, saving a distance up to a millimeter. And so we modeled this here. We said, whatever the void width is, for 3 times the width of the void distance, we have a K of 40. Then from 3 to 10 times, a K of 20. Beyond that, a K of 10, which is that of alumina. Because the fact that manganese titanium is penetrating into the alumina, we think was increasing the relative permittivity there, because it certainly increased the holdout voltage. That's an aside, which later on, because we'll discuss about one of the ways of improving flashover voltage, surface flashover, is treating the surface of the aluminum, of the insulator. And we find treating the surface, because the manganese titanium penetrated, we made what we call the quasi-metallized. In other words, it was the moly manganese titanium metallized, but we left out the moly. So if you apply manganese metallized to the surface of the insulator, it penetrated in, but there's no conductive layer. But what did do on our insulators, so first of all, it increased the surface conductivity. I mean, it's still very high resistivity, but allowed surface charge to drain off faster. And also, we think there was suggestions, so we didn't measure it directly, it decreased the secondary electron coefficient of the surface. Anyway, treating the surface of an insulator with a manganese titanium mix, which we call the quasi-metal, significantly improve the hold-off voltage. So now, as we discussed earlier, the final flashover in insulator occurs in desorbed surface gas. So we did an experiment then years ago. This happens to be one of the inverted alumina insulators, which I did a lot of work with. We did two tests. One is we assembled the alumina insulators and tested, flashed them over, then baked them out and retested them. The second series, we baked out the start and then exposed the atmosphere and retested. The results for both series were identical. The flashover voltage, of course, for the baked insulator was considerably higher than for the unbaked insulator. But if you measure the amount of gases emitted, the baked insulator with no flashover is a very small amount. Because again, remember with the conditioning, you're getting, particularly if an insulator hasn't had too many, you increase the voltage until you get a flashover, and then you can apply the same voltage and you won't get a flashover. So in this case, with a baked insulator, when you get a flashover, we get typically 25 to 32 of these units. With no flashover, it's very, very small, we could barely see it. With an unbaked insulator, you got much more, proportionally significantly more gas involved, even with no flashover. But the amount of gas involved for flashover was of the same order. Remember, these are identical insulators. The only difference are they're baked and not baked, and the baked at a higher flashover voltage than not baked. But the important thing here is, while the baked high flashover voltage was significantly higher than the not baked, the amount of gas necessary released when flashover occurred was of the same order, indicating these particular setup, you need a certain amount of gas absorbed to have flashover. If it's baked, you have to have, to get that amount of gas, it took a significantly higher voltage. Now, normally you don't worry about magnetic fields, but of course, particularly in accelerators, there's going to be significant magnetic field presence. So the effect of magnetic fields and surface flashover has to be considered. This is a typical, but this is a typical experimental result. Also agrees with calculations. If a flashover voltage has no magnetic field, if your slight magnetic field is driving the emitted electrons into the insulator, you decrease the voltage somewhat. Then as you're driving them in faster, it increases. Very similar to the effect of cone angle. Similarly, if the magnetic field is pulling the electrons away from the surface, it's improving the hold-off voltage and then approaches saturation. This is because you have to consider this because particularly in accelerators, large accelerators, their magnetic field presence, and you have to consider which their magnitude and direction in the surface of your insulators. To conclude, this talk, I presented theoretical predictions and experimental results and methods to improve surface flashover voltage of insulators. The theoretical prediction, one very critical one, was the importance of the cathode triple junction. So you want some techniques to decrease the microscopic field. Well, you can shape the electrodes, you can shape the insulators, recess the insulators and the electrodes, put metal inserts in the insulators. And one thing I didn't discuss, but used particularly in circuit breakers and such, is external metal shields. Then you also want to decrease the microscopic field. Again, minimize the voids at the triple junction. One of the ways you can do a bit of this with organics that doesn't work with ceramic is having a increasing pressure on the insulator, which will tend to minimize the voids. Graded permittivities, it's shown this is an effective way of reducing the effective voids. Bonded interfaces, again, possible primarily very tightly bond with organics, pressure in soft insulators, and conditioning insulators, because I think you're burning off triple weak points of the triple junction, and also revolving surface gas. And again, the importance of desorbed burning off weak point. Again, the importance of desorbed surface gas for flashover. Minimize the quantities of the absorbed gas. The insulator material, some materials absorb more than others. Fire the insulators before assembly. You can effectively, mainly with ceramics, assemble systems in clean conditions. This is always important. Baking out the systems, even organics can often be baked, say, at 100 degrees. While ceramics are typically baked at 300 or 400. And conditioning the insulator again. Minimize the area available for absorption. Again, surface treatments. Reduce surface damage during fabrication. Be very careful, because any surface scratches and such give you more surface area. Plus, they also make it, the damaged surface is often more likely to absorb gas. Minimize the binding energy of the absorbed gases. Surface treatment can do this, and this is one of the ways we think the quasi-metallized technique works. To conclude, the summary, I reviewed surface flashover insulators in vacuum, presented theoretical mechanisms for surface flashover, pertinent experimental results. Conclude the field emission from the cathode triple junctions, the primary initiating mechanism of surface flashover insulators vacuum. Although with suitably non-uniform fields, the flashover originated the anode triple junction. I didn't mention that particularly, but you consider like an ion microscopes, where effectively a large cathode and a needle anode surface or breakdown. In this case, vacuum breakdown can occur by just disruption of the anode. So it's possible, depending the geometry, that with extremely high fields at the anode triple junction, you could flash over starting there. Normally, flashover is developed by a secondary electron emission avalanche, although the present density of shallow and deep traps can significantly affect the secondary electron emission. The final stage of flashover occurs in desorbed surface gas, possibly including vaporized insulator material with organic insulators. I then discussed the implications for the practical applications with flashover. Showed the life of insulators depends upon many parameters. The properties of the insulator itself, its material, its geometry, its surface finish, how it's attached to the electrodes, the applied voltage, whether it's a pulse, the duration, whether it's a single pulse or repetitive, and of course, the duration could be AC, and the history of the insulator, how it was processed, what's operating environment. Material geometry when choosing a particular application. Techniques for specific techniques were mentioned. Well, that finished, and thank you for your time, and open for questions now. Let's see.
Thank you so much, Dr. Miller, for the great presentation. We learned a lot. I personally did. So we have a question in the chat box by Dan Schweikart. And he says these breakdown phenomena apply to very high vacuum environments. At what higher pressure level does one need to consider other breakdown mechanisms in the gaseous media?
Okay, well, we did some work with extremely high vacuum because particularly with vacuum interrupters, once you've made these things, they have to sit for years. So you have to have a high clean vacuum, but actually vacuum down to, oh, I always get confused, 10 to the minus 3 torr, a thousandth of an atmosphere or so. It's when the gas tends to become, you have to worry about gaseous breakdown. Before that, you have to consider, because, you know, even though gaseous breakdown isn't occurring, there's enough gas present that's going to be coating the surface. So you'll have, additional, much more adsorbed gas present. And this is then affecting the surface flashover, even though you aren't getting flashover in the atmosphere, but it's affecting the surface flashover because you're having thicker layers of absorbed gas.
Thanks a lot for your response. Please feel free to put your question in the chat box or raise your hand, or I don't know if everybody is permitted to unmute themselves, but if you can, please feel free to ask your question. I have a question myself. Yeah, is there any problem?
Well, the one thing I forgot to put my last slide on, if anyone is particularly interested. This paper is developed upon 2 review papers I wrote. One not too long ago, well, 2015, it's 8 years now. My original one was written in the 90s, and then the second paper was 20 years of flashover results, and I think it's still the most current review. Both papers are useful together because some things I covered in detail in the first paper and with figures, which I just referred to briefly in the second paper, because, editors like to have length limits when you have a published paper. So the 2 were actually complement each other. Unfortunately, I forgot to put that on. All right,
I'm sure if people look up your name in the internet, they will be the first papers showing up. I have actually a question about different methods of conditioning the surface of the insulator and electrode, actually. We know that one method is gradually raising the voltage and burning off all the weak points, as you mentioned. But there's some other methods like plasma conditioning or spark. Is your experience like showing any like superiority between from these methods compared to the gradual voltage increasing method?
Well, actually, there's no real particular reason. They complement each other.
Mm-hmm.
I prefer not use it, but I've known people and read papers where they do things like plasma cleaning, or and similar results, but they complement each other. It's good to clean the surface, but you can also, do conditioning. In other words, they are not opposed. That you can use them both. It depends. It's often they clean the surface before they're assembled, and then assemble it, and then clean them. Also, sometimes you clean the assembled surface, or the final stage, often before you use, say, like a plasma cleaning, then you evacuate and bake out, and then condition it and put it in service. So, I didn't mention that at all, because, but it is, they're complementary. You can use them both.
Awesome, thank you. Actually, one more question. You mentioned the effectiveness of baking in removing a lot of absorbed gas potentially in the 3rd stage of flashover. Was there like a threshold or like a relationship between the temperature of bake out or like a minimum temperature, for example, for ceramics, that the temp?
Oh, very, very, very strongly, as I said, with ceramics, 100 or 200 degrees. But if you bake the ceramic to 400, we typically did 400 in our setup. That got more gas off, and that was sufficient. I mean, if you went higher, you might have gotten more off. But for our applications, much of my work was done or related to vacuum interrupters, which have to be assembled, particularly underground. One of their big advantages, you put them underground and they can sit there for years. And one of the things they have to do, sit there for years, they may never operate for 10 years out. All of a sudden there's a lightning strike. Now the interrupter has to work for the first time, and it better work right the first time, and they do. That's why they're so popular. But 400-degree bakeout was sufficient to get it down to the point where could go many years before the pressure got up to a point it was a problem.
Yeah, great.
And
we also have,
even with organic insulators, you can often say bake them at 100 degrees C or so, which was significant helps.
Yeah, especially I think like removing the content of water probably is, we also have another question from Abdul Latif. He asked, could you elaborate more on using manganese titanium to treat the surface at the cathode triple junction?
Okay, well,
does this treatment affects the insulator? Sorry, the question actually continues a little bit more. Does this treatment affects the insulator breakdown strength itself? And is this technique also applied to the anode triple junction? Moreover, is this a treatment also used with nano-doped insulators?
Well, as I said, we found experimentally, because we happen to be routinely using a moly-manganese titanium, and occasionally we use another one and found out, oh, the moly-manganese works a lot better. Why? And then we actually, when I said we did the quasi-metallizing technique with just with the manganese titanium. I think the original ratio was 7 manganese to 1 titanium. I could be wrong. I have my paper here, but I'm talking, not looking it up. We varied that it was tolerant. The original ratio could be varied somewhat and was equally effective. But when we did the quasi-metallizing, we actually cracked the ceramic and looked at it with the technique and showed that you could see the manganese titanium actually penetrated into the surface up to 1 millimeter. So, a significant penetration. So therefore we assumed this is also occurring at the anode cathode triple junction. In our application, the anode triple junction wasn't necessary, but it was necessary to assemble. You needed to metallize the anode as well. So it would have been the same, but in our application, the anode triple junction was not a weak point.
There's also another question.
In my review paper, we did publish a couple papers on the quasi-metallized, and they're mentioned in my review paper. So,
yeah, great. There's also another question from John K. Did your experiments with adding material strips in the evacuated space of a vacuum insulator to absorb any gases released over time?
Oh, no, we did not do that. But that is very commonly, particularly often sometimes with interrupters, you have like there's a getter put in when they're assembled. That's a common technique. We didn't happen to use it because our devices were fairly small, particularly in larger devices. That's a common technique. You put a getter in. As I said, I didn't mention it because with our small devices, A, it wasn't necessary, and B, it would have been a little tricky to put it in. But larger devices, yes, that's routinely used.
Great, thanks a lot for your answers.
And particularly, I guess you can also post, my email address if people have questions or so. I'm happy to answer.
Sure. I think I have it. I can look it up and put it in the chat box.
Oh, yeah. No,
Also, another question. As a result of this research, has there been any recent increase of the rated voltage of vacuum interrupters?
I'm sorry, what was the question again?
As a result of this research, has there been any recent increase of the rated voltage of vacuum interrupters?
Not necessarily as a result of my work, but I know there's considerable work been done, particularly in Asia and China and Japan, of extending to higher voltage, getting up and, instead of the local 2430, take you 24 to 32,000 volts for distribution, going up to 110 or 150,000 volts, trying to get up to more transmission. But normally a lot of this research, you're trying to, instead of having, they're used in more than one vacuum interrupter in series. But I know there's a lot of work has been done in Asia and going to much higher voltage.
Thanks again. I think we're almost done here. Yeah, thanks for posting your email. Dr. Miller's email is being shown in the chat box. And I want to thank you again for taking your time. Really, I think absolutely learned a lot in this presentation, and we're hopeful that we can have you later. I think we can learn a lot more in future. I think there are more grounds, especially as someone can read from your papers, that there are other areas with vacuum insulators and flashover that can be impactful. So thanks again, everybody. As I mentioned earlier, next month we're going to have Dr. Greg Stone for our next webinar, and as always, it's going to be in the second Tuesday of every month. Thanks again for your time, and hope to see you soon.